Hello, welcome to another Midnight Maths video. In this one, we're going to be looking at rotations and just how you rotate stuff, how you calculate volumes more specifically, with revolutions. So in this video is going to be a quick conceptual overview, and then in future videos we'll go over some examples. So usually what happens is, as always with calculus, we start with some sort of function, okay? And we call this, y equals f of x. And what we really want to do is, you take this shape, say this weird shape, and then you pick, let's say it's some shape like this, And then what you do is you pick some axis, like you say, let's go with this axis here. And then you sort of rotate the shape about the axis. So, what we want to do is take this guy over here and sort of mirror him. So mirror him this way. And so, you can sort of imagine this would be his mirror image, this here, and then I'll draw some of that outline of this shape. So it's kind of a weird shape, and typically with solids of revolution and calculus, we try to find the volume of weird shapes like this. So what we do is, well, this is indeed a weird shape that we can't use any formula on, but as is typical with calculus, we just split this up. And if you take this very small rectangular piece and rotate it about the axis, it's gonna be basically a cylinder. And that's really where the heart of this. Now, of course, this particular rectangle I've drawn here, it might not be exactly a cylinder, but as you get smaller, and then eventually you use integral calculus to get really small, then the approximation becomes better and all of that. So since we're working with cylinders, it would help if we knew the volume of one cylinder. So typically we work with really skewed cylinders like this one. And, just a bit of review, if you have some sort of radius r and then some sort of height h, then the volume of the cylinder is going to be the area, just pi r squared, so that's the area of this face right here, and then you scale it up by the height, so multiply by h. So you get pi r squared h for the volume of this thing. So that's all we're going to do over here. So, but of course, we can't just find volumes of random stuff that's drawn. So in calculus, we usually need some sort of function. So we come back to our function here. And, we pick some sort of axis as usual. And then usually we bound the region. So let's say from point, this is A right here. So that's x equals a, and then we go all the way to x equals b, and we say, they usually call it r, let's rotate this region r right here about this axis. And so the first thing, which I'm going to do, and which you should probably do when you're solving a problem like this, involving this sort of thing, is to draw. So here I'm drawing each of these little cylinders that we are cutting r into. So when we found areas, we would cut r into these rectangles for area, right? Like finding this area is pretty straightforward, but to do this cylinder thing, we just pretend like this right here is the radius. Then you rotate. So you rotate this small little rectangle, and then sort of, so this is sort of its mirror image, and then you can draw the, so hopefully you can visualize sort of what this small piece looks like. And if not, there are better visualizations online that you can look at as well. And here you see we've got, in this little circle, we've got basically a very short but stout cylinder, right? So it's going to have a radius of r at this particular point, and it's also going to have a very small height. And the thing is, we usually integrate, right? We integrate from a to b. So this height we call like h. We would call h in the formula, and then we usually just say that's dx. Can be dy as well, but in this case we're talking about dx because it's a small change in x. That's what this whole rectangle sort of implies, that the the small width of this rectangle is dx, and then the height is f of x, like at that point, wherever, if it's this point or that one. So the end result is you basically just do pi r squared h, right? Well, not just this particular one, right? Because this is just one of many cylinders, but we want to rotate this rectangle as well, and we want to rotate this one. I'm draw that in red. You want to rotate like this rectangle as well. Now, I do apologize, these are quite... Let me make these rectangles neater here. So, for example, you'd also rotate this one, this rectangle, and this rectangle would have its own, mirror image, and then, you can rotate it like that, and, so you have all these rectangles to add up. So you added up all of them, and then you add them up from A to, B. So from A to B. Now, this is basically where the formula comes from. You have integral from A to B, so integral is basically just a super adding, and then you're adding pi. Now r, here's the thing, in the initial presentation, in this formula, r is just some constant number that doesn't change, so you just multiply by h. But now over here, r is actually, it changes depending on where you are, whether you're right here or right there or so on. R is actually a function. Now, the function might not be this function per se, this exact f of x, but it's probably related to f of x in some way. But it's in this particular case, especially, it's not exactly f, so I'll call it some sort of other function, r of x. And probably the heart of this whole thing, this whole method, is figuring out what that r of x is exactly. And then, do not forget to square. So pi r squared, right? And then you've got h, which we said h was the dx every single time. So you have dx. So this is essentially, rotating. This is probably the important formula. And the bad news about rotation is that there are a whole bunch of little subcases, and it seems like you have to memorize a whole bunch. But the good news is that all the subcases are actually just based on this single formula alone. So if you really understand visually what this formula means, and like how you go about actually computing it, then the other subcases aren't too bad. So, for example, in this case, it was really convenient because our radius always touches the axis. The tip of this tip is always touching this axis. Now, all these building blocks are going to be like that, where the radius touches the axis. But sometimes the problems will ask you, like the problem might ask if this, let me remove all this stuff here. So if all this is r, now maybe they don't want this particular axis right here. Maybe they want something different. Maybe they want you to rotate it along about this red axis right here. So now it's a different story. if you rotate this region about this axis, it's disconnected from the region now, what are you going to get? Well, you're not going to quite get a cylinder like we got last time. You're actually going to get this weird washer looking thing. So you have like this rectangle, right? Now, this mirror image, I can't just put it over here. It has to go all the way, you know, maybe right there. So, and then you have this whole deal, right? Where you have sort of looks like this. I do apologize, the drawing's not the best. But again, if you're having trouble visualizing it, there are a good amount of online visualizers that really like actually draw the whole rotation so you can see. I might link a few of those in the description. But if you can picture with this pretty bad drawing that I have here, it's a washer looking shape, and now instead of adding like all the cylinders, we're going to add all the washers. Now you might ask, well, how is it all based on this? We're going to have to modify it, right? Well, yes, we are, but it's going to be a little different. Basically, what we do is, let me just clear off this. We take this. Now remember, I did say that all the subcases are based off of this, right? So we do something a little bit clever where we take this whole thing and just like if you had these pink rectangles and then instead of rotating, we know we want to rotate like these red rectangles that I've drawn here, but what we'll do for now is we'll rotate the pink rectangles. You get like more of that cylinder looking ish thing that we dealt with in the last example. You rotate this, so now we just get right the same thing. And I won't draw the connector, but hopefully the mirror image helps you visualize. And then afterward you cut out the portion that the excess portion. So you have this big guy, and then you rotate it, and then afterward you cut like this portion, say. Cut, let me sort of highlight where we're going here. We're cutting this guy. So that's actually just like a cylinder, right? This would be like a yellow cylinder, and then we'd mirror that highlight over on this side. So that's sort of the shape that we'd be cutting out, is the yellow part. Now, the thing is, cutting out in math, this is just going to mean subtracting. So you start with this big volume. This whole thing might have a volume of like 50, and then this yellow cylinder might end up having a volume of 30. So then you cut out the volume of 30 from the volume of 50. You subtract it, and then you would get that your total whatever is left, which is this stuff rotated about the red line. That is going to give you a volume of like 20 in this case. So it's basically the same thing. It's basically you just do this twice. So now what you have is you have whatever your integration is from a to b pi. Now I'll keep the capital R squared dx. So this R is like a big R because we had like a bigger shape than before. So for example, that might be this guy right here, R of x. This function R of x is different from like the region R, right? But this function R of x, when you rotate it, it's going to give you a volume that's bigger than what you want. So you subtract another volume, and it's going to have the same form as this base guy, except now we have a smaller r. So this smaller r we'll call like rx squared dx, and that's just going to be like, in this example, that's going to be like this right here. So this is r of x, small r of x. And let me remove big R for clarity. So the small r of x, now in this case, it happens to be constant throughout the whole AB, right? So one time at this x, it's that, and at this x, it's also that. But that may not be the case where you have like a constant r function, so you leave it as a function. And this right here is, you know, basically the other formula that you use. So of course, there are variations depending on whether you integrate with respect to x or with respect to y or whatnot. But really, in your head, you only need this singular formula right here, or at the very most, both of these formulas here. But really, the second one is just two versions of the first one, right? So it's really important in these sorts of problems to, you know, there's like the geometry portion of it, and then there's the calculus. So don't let the calculus ruin the geometry, right? Or vice versa. Just make sure you have like a solid understanding of what the geometry is. That's what I hope this video will give you. And in future videos, we're gonna, like, you know, actually do some computations, do some calculus. But remember, even when we do the calculus, we start with the geometry first. We'll always start with rough pictures like the one I've drawn here. So hopefully this video gave you a better geometric feel for what volumes of revolution are actually doing. In future videos, we'll do some FRQ problems, so hopefully you can see how this is actually used in practice. And I will see you guys then.